there is something very strange happening at the largest planet in our solar system. For decades, Jupiter has looked calm from a distance, a bright, steady giant hanging in our night sky. But once NASA sent a probe straight into its orbit, everything we thought we knew about this world started to fall apart. Because beneath those beautiful bands of clouds, something is moving, something deep, massive, and completely unlike anything we've ever seen on a planet before. We're talking about storms the size of continents locked in perfect geometric formations, winds that dive thousands of miles into the planet. And at the center of it all, a core that shouldn't exist. None of this was visible from Earth. It only came to light after NASA launched a spacecraft with a single goal: get underneath Jupiter's clouds and uncover whatever the planet has been hiding for billions of years. That spacecraft was called Juno, and what NASA's Juno found shocked everyone. In 2011, NASA launched one of the most ambitious missions in the history of planetary exploration. The spacecraft was called Juno, named after the Roman goddess, who could see through clouds and mist to reveal her husband Jupiter's true nature. The symbolism was deliberate. Juno was built at Lockheed Martin's facilities in Denver, Colorado. The spacecraft had a distinctive design shaped like a hexagon, with 3 massive solar arrays extending from it like the blades of a fan. Fully deployed, Juno would span more than 66 feet across. This was the first solar-powered spacecraft ever designed to operate at Jupiter's distance from the Sun. Out there, sunlight is 25 times weaker than on Earth. To generate enough power, each of Juno's 3 solar arrays measured nearly 30 feet long, but solar panels were just the beginning. Juno carried 9 scientific instruments, each designed to probe a different aspect of Jupiter. There was a microwave radiometer to measure water and ammonia deep in the atmosphere, an infrared mapper to study auroras and surface temperatures, a magnetometer to chart Jupiter's magnetic field in unprecedented detail, and then there was JunoCam, a visible light camera included specifically for public outreach. NASA wanted everyone to see what Juno would see. The spacecraft also carried something unusual: a titanium vault. This armored box, weighing 400 pounds and about the size of an SUV trunk, housed Juno's most sensitive electronics. Because Jupiter is surrounded by a radiation environment more hostile than anywhere else in the solar system, except the Sun itself. Jupiter's magnetic field is the strongest of any planet, 15 times more powerful than Earth's, and in some places, more than 50 times more intense. This field traps charged particles and accelerates them to extreme energies, creating radiation belts that would fry unprotected electronics in minutes. The titanium vault would shield Juno's computers and instruments from this barrage. But even with that protection, the mission had a limited lifespan. Eventually, the radiation would win. On the 5th of August 2011, an Atlas V rocket lifted off from Cape Canaveral, carrying Juno toward the outer solar system. The journey would take 5 years. Getting to Jupiter isn't straightforward. You can't just point a spacecraft in the right direction and light the engines. The distances are too vast, the energy requirements too extreme. So mission planners used gravity. After launching, Juno first traveled outward past the orbit of Mars. But then it did something strange. It turned around and came back toward Earth. In October 2013, Juno swooped past our planet at an altitude of just 347 miles, moving at over 78,000 miles per hour. As it passed, Earth's gravity pulled on the spacecraft, accelerating it like a cosmic slingshot. This gravity assist added 16,330 miles per hour to Juno's velocity. That extra speed was exactly what the spacecraft needed to escape the inner solar system and reach Jupiter. Without that maneuver, Juno would never have made it. For the next 3 years, the spacecraft coasted through the darkness of deep space, its systems mostly dormant. Its solar arrays turned toward the distant Sun, gathering just enough light to keep the electronics alive. And then, on the 4th of July 2016, Juno finally arrived. Arriving at Jupiter and entering orbit are 2 very different things. Juno was traveling at over 165,000 miles per hour when it reached Jupiter. At that speed, the spacecraft would simply fly past the planet and continue into deep space. To enter orbit, Juno needed to slow down. And that meant firing its main engine at precisely the right moment for exactly 35 minutes. There was no room for error. Too early, and Juno wouldn't have enough fuel for a second attempt. Too late, and the spacecraft would miss Jupiter entirely. And there was another problem: distance. Radio signals from Juno took 48 minutes to reach Earth. By the time Mission Control received any message, it would already be ancient history. There was no way to send last-minute corrections or adjustments. Juno would have to execute the entire sequence autonomously. At 11:18 p.m. Eastern Time on the 4th of July 2016, Juno fired its main engine. For 35 minutes, the spacecraft slowed itself down, fighting against its own momentum while Jupiter's gravity pulled it closer. Mission Control watched telemetry trickle in from nearly 500 million miles away. And then, at 11:54 p.m., confirmation arrived. The engine burn had completed. Juno was in orbit. The spacecraft had arrived within 1 second of its predicted timing. After a 5-year journey across 1.7 billion miles, that level of precision was extraordinary. Now the real work could begin. Juno's orbit was unlike any planetary mission before it. Previous spacecraft that visited Jupiter, Pioneer, Voyager, Galileo, Cassini, all approached the planet along its equatorial plane. They saw Jupiter from the side, the same view we get from Earth. Juno would be different. The spacecraft's orbit carried it high above Jupiter's north pole, then plunged down between the planet and its radiation belts, skimming just 2,200 miles above the cloud tops at its closest approach. For context, if Jupiter were the size of a basketball, 2,200 miles would be less than a quarter of an inch. From this vantage point, Juno could peer directly down at the poles regions of the planet that had never been seen up close. On the 27th of August 2016, Juno completed its first science pass. JunoCam began transmitting images. What scientists saw stunned them. Jupiter's north pole was covered in storms. Not the organized bands and zones visible from the equator, but a chaotic, swirling mass of cyclones packed together in strange geometric patterns. At the center sat one massive storm. Around it, 8 more cyclones arranged themselves in a near-perfect octagon. Each storm was the size of Earth or larger, and they weren't drifting. They weren't merging. They just sat there, locked in formation. At the South Pole, the pattern was different but equally strange. 5 cyclones surrounded the central vortex, forming a pentagon. No one had predicted this. On Earth, cyclones move. They form, travel across the ocean, and dissipate. The idea of giant storms staying locked in geometric patterns for years, possibly decades, was unprecedented. And this was just the beginning. Jupiter's magnetic field had always been known to be powerful. But Juno's magnetometer revealed just how strange it really was. Most planets with magnetic fields generate them through a process called a dynamo. On Earth, liquid iron in the outer core flows and creates electric currents. Those currents generate a magnetic field that extends into space, forming the magnetosphere. Jupiter should work the same way. But instead of molten iron, the conductor is metallic hydrogen compressed so intensely by pressure that its electrons break free and flow like a metal. Scientists expected Jupiter's magnetic field to be strong but relatively simple. A clean dipole, like Earth's, just much bigger. That's not what Juno found. Jupiter's magnetic field is lopsided. It's far stronger in the northern hemisphere than in the southern hemisphere. And scattered across the planet's surface are patches of intense magnetism that don't fit any simple model. One of these patches, located near Jupiter's equator, became known as the Great Blue Spot. The Great Blue Spot isn't visible to the eye. It's a region of exceptionally strong magnetic flux, an isolated, intense patch embedded in Jupiter's magnetic field. And it moves. Juno tracked the Great Blue Spot over multiple orbits. The feature was drifting eastward, pushed by powerful winds that extend thousands of miles below the cloud tops. At the surface, Jupiter's winds can reach speeds over 400 miles per hour. But Juno's data showed that these winds don't just blow across the top of the atmosphere, they penetrate more than 1,900 miles deep, reaching all the way down to where the hydrogen transitions into its metallic form. Those deep winds appear to be dragging the magnetic field with them. This creates something called secular variation changes in a planet's magnetic field over time. Before Juno, scientists had only ever confirmed secular variation on Earth. Now they were seeing it on Jupiter. But here's the strange part. The changes Juno measured were tiny. So tiny that it took decades of data comparing measurements from Pioneer. The Great Blue Spot is responsible for most of Jupiter's secular variation. But why it exists in the first place and why it behaves the way it does remains unclear. Scientists suspect it's related to Jupiter's interior structure. But to understand that, Juno needed to look deeper. Planets keep their secrets buried deep inside. For Jupiter, those secrets have been hidden beneath thousands of miles of gas and liquid hydrogen. No telescope can see through it. No probe can survive the journey down. But there's another way to look inside a planet. Gravity. Every bit of mass inside Jupiter pulls on objects around it. By measuring how Jupiter's gravity tugs on a passing spacecraft, scientists can reconstruct how that mass is distributed. Juno's orbit was designed specifically for this purpose. Each time the spacecraft skimmed past the cloud tops, scientists tracked its radio signal with extreme precision. Any change in Juno's speed, even a shift of less than a millimeter per second, revealed something about the mass beneath. And the data revealed something unexpected. For decades, scientists had two competing theories about Jupiter's interior. The first suggested that Jupiter formed through gravitational collapse gas from the early solar system simply pulled itself together under its own weight. In this model, Jupiter would have no core at all, just layers of hydrogen and helium stacked endlessly toward the center. The second theory, called core accretion, proposed that Jupiter started with a solid nucleus, perhaps 10 times the mass of Earth, made of rock and ice. Once that core was in place, its gravity pulled in surrounding gas, ballooning into the giant planet we see today. Both theories made sense. Both had problems. Juno's gravity measurements showed that neither theory was quite right. Jupiter does have a core, but it's not a solid, compact ball of rock. Instead, it's diffuse, fuzzy. Heavy elements are concentrated toward the center, but they blend gradually into the surrounding hydrogen and helium without any sharp boundary. This wasn't what anyone expected. The discovery of Jupiter's fuzzy core forced scientists to rethink how giant planets form. In the clean models, a planet should have distinct layers: a dense core, a liquid mantle, a gaseous envelope, each layer separated by a clear boundary. Jupiter doesn't follow that rule. Juno's data suggests that heavy elements oxygen, carbon, nitrogen, silicon are spread throughout a vast region spanning roughly half the planet's radius. Instead of sinking into a compact core, they appear to have mixed with the surrounding hydrogen over billions of years. But how? One idea is that Jupiter was hit by another massive object early in its history. A collision with a planet 10 or even 20 times the mass of Earth could have shattered a once solid core, scattering heavy elements outward and mixing them into the surrounding layers. Computer simulations tested this scenario. Researchers modeled thousands of impacts at different speeds and angles. The results were consistent. Yes, a giant impact would disrupt the core, but over time, gravity would cause the heavy materials to sink back down and reassemble into a compact core. The simulations couldn't produce a fuzzy core that stayed fuzzy for billions of years. So scientists turned to another explanation. Maybe the fuzziness is original. Maybe it's a natural outcome of how Jupiter formed. In this view, as Jupiter accumulated mass, heavy elements didn't just sink and lock into place. They partially dissolved into the hydrogen and helium envelope, creating gradients instead of sharp boundaries. Another key factor is convection. On Earth, convection keeps the mantle churning, mixing material and spreading heat. If Jupiter's entire interior were convective, any compositional gradients would eventually be erased. But Juno's measurements suggest that large parts of Jupiter's interior are stable, meaning they don't mix efficiently. That stability allows the fuzzy core to persist, and Jupiter isn't alone. After Juno's discovery, scientists wondered whether fuzzy cores might be common among giant planets. Saturn was the obvious place to look. NASA's Cassini spacecraft orbited Saturn from 2004 to 2017, collecting years of data before its mission ended in a deliberate plunge into the planet's atmosphere. Cassini didn't carry the same gravity-measuring instruments as Juno, but it had something else: Saturn's rings. Saturn's rings aren't just beautiful, they're seismographs. Vibrations inside Saturn ripple outward and disturb the rings, creating tiny waves that can be measured. By studying those waves, scientists can probe Saturn's interior, much like seismologists use earthquakes to map Earth's core. When researchers analyzed Cassini's ring data alongside gravitational measurements, they found the same pattern. Saturn has a fuzzy core, heavy elements concentrated toward the center, but gradually blending outward without a sharp edge. This was a turning point. If both Jupiter and Saturn share this trait, it's unlikely to be a coincidence. Fuzzy cores may be a natural feature of how giant planets form. And if that's true, it changes everything we thought we knew about gas giants across the galaxy. While Juno was revolutionizing our understanding of Jupiter's interior, JunoCam continued to capture images of the planet's surface. And the polar storms remained one of the mission's most enduring mysteries. At the North Pole, 8 cyclones surrounded a central vortex in a perfect octagon. At the South Pole, 5 cyclones formed a pentagon around the center. These storms have been stable since Juno's arrival in 2016. They don't drift, they don't merge. They just spin in place, their spiral arms smashing together without combining. Only once did something change. In July 2019, 2 of the southern cyclones began to move apart. A gap opened between them, and in that gap, a 6th cyclone appeared. For about 6 months, the southern storms formed a hexagon. Then, as suddenly as it appeared, the 6th cyclone vanished. The structure returned to its original pentagon configuration. Scientists still don't fully understand why the polar cyclones behave this way. One theory suggests they're held in place by rings of anticyclonic winds that rotate in the opposite direction, acting like barriers to keep the cyclones from drifting. Another idea is that the cyclones are deep, extending thousands of miles into Jupiter's interior, rooted in convective flows driven by heat from below. If the cyclones are shallow, they should move with the surface winds. But measurements show that both the northern and southern storm patterns rotate much more slowly than the winds around them. At the North Pole, it would take roughly 100 years for the octagonal pattern to complete one full rotation. At the South Pole, about 50 years. That slow rotation suggests the cyclones are anchored by something deep inside the planet, but the details remain unclear. Jupiter isn't just a planet, it's a system. Orbiting the giant world are at least 95 known moons. 4 of them, Io, Europa, Ganymede, and Callisto, are large enough to be considered worlds in their own right. Galileo Galilei discovered these 4 moons in 1610, making them the first celestial bodies ever confirmed to orbit another planet. They're called the Galilean moons in his honor. During its extended mission, Juno flew close to 3 of them. In June 2021, Juno passed within 652 miles of Ganymede, the largest moon in the solar system. It was the closest any spacecraft had come since Galileo's flyby in May 2000. In September 2022, Juno flew by Europa, the ice-covered moon believed to hide a liquid water ocean beneath its frozen surface. And then came Io. Io is the most volcanically active world in the solar system. With more than 400 active volcanoes, the moon is constantly reshaping itself. Lava flows, ash plumes, and sulfur deposits cover its surface in shades of yellow, orange, and red. The source of all this activity is Jupiter itself. Io orbits extremely close to the giant planet, just 262,000 miles away. For comparison, our moon is 238,000 miles from Earth. But unlike our moon, Io's orbit isn't circular, it's slightly elliptical. That means Io's distance from Jupiter changes as it travels around the planet. And as the distance changes, so does Jupiter's gravitational pull. When Io is closer, Jupiter's gravity squeezes the moon. When it's farther away, the pressure lessens. This constant kneading generates immense heat through friction, melting rock deep inside Io and driving its endless volcanism. In December 2023 and February 2024, Juno made its closest passes of Io within 930 miles of the surface. The spacecraft's infrared instrument, GRAM, scanned the moon's southern hemisphere, and it detected something extraordinary. A massive volcanic hotspot larger than Lake Superior, spanning more than 40,000 square miles. The feature was emitting more than 80 trillion watts of energy. That's 6 times the total output of every power plant on Earth combined. Scientists had never seen volcanic activity this intense. The data suggests the hotspot isn't a single volcano, but several closely spaced eruptions happening simultaneously, possibly fed by a vast underground magma chamber. This discovery broke the previous record held by Loki Patera, a lava lake on Io measuring about 7,700 square miles. When Juno flew past Io again in late December 2024, GRAM looked at the same region. The hotspot was still there, still erupting. Visible light images from JunoCam showed that the landscape around the hotspot had changed. The surface coloring was different evidence of fresh lava flows and volcanic deposits. Eruptions, this large leave long-lived signatures, pyroclastic deposits, sulfur-rich plumes, lava flows fed by underground fissures. Juno will continue monitoring Io through the end of its mission, scheduled for September 2025. What scientists learn from Io could help them understand volcanic processes not just on other moons, but on rocky planets throughout the galaxy. Jupiter's magnetic field doesn't just create radiation belts and strange magnetic anomalies. It also generates auroras. Like Earth's northern and southern lights, Jupiter's auroras form when charged particles collide with atoms in the upper atmosphere, releasing energy as light. But Jupiter's auroras are far more powerful. The most energetic auroral particles on Earth carry a few thousand electron volts. On Jupiter, they reach 400,000 electron volts. These auroras aren't triggered by solar wind alone. Jupiter generates many of its own charged particles, pulled from volcanic eruptions on Io and other sources within the magnetosphere. Juno's ultraviolet spectrograph captured detailed images of the auroras at both poles. One of the mission's key discoveries involved Jupiter's moons. As the Galilean moons orbit through Jupiter's magnetic field, they leave distinct auroral signatures in the planet's atmosphere, footprints of glowing light tracing their paths. Before Juno, scientists had observed auroral footprints for 3 of the 4 Galilean moons: Io, Europa, and Ganymede. But Callisto, the outermost of the 4, remained a mystery. During a targeted observation, Juno finally detected Callisto's auroral footprint. All 4 moons now accounted for. No feature on Jupiter is more iconic than the Great Red Spot. This massive storm has been swirling in Jupiter's southern hemisphere for at least 350 years, possibly longer. When the Voyager spacecraft flew past Jupiter in 1979, the Great Red Spot was large enough to fit 2 Earths inside. By the time Juno arrived in 2016, it had shrunk. Now it's only 1.3 times the diameter of Earth. The storm is still shrinking. But how deep does it go? Juno's microwave radiometer can peer through Jupiter's clouds, measuring temperature and composition at different depths. The data revealed that the Great Red Spot extends more than 200 miles into Jupiter's atmosphere, 50 to 100 times deeper than Earth's oceans. That depth helps explain why the storm has lasted so long. On Earth, hurricanes lose energy when they pass over land or encounter changing wind patterns. But Jupiter has no land, and the Great Red Spot draws energy from heat rising up from deep within the planet. As long as that heat source remains, the storm will continue. But scientists still don't fully understand why it's shrinking. Jupiter's atmosphere is divided into bands alternating stripes of dark orange and light gray, called belts and zones. For decades, scientists debated how deep these bands extended. Were they shallow features, confined to the top few hundred miles of the atmosphere, or did they penetrate much deeper? Juno answered that question. By measuring Jupiter's gravity field with extreme precision, Juno determined that the belts and zones extend roughly 1,900 miles below the cloud tops. At that depth, the pressure becomes so intense that hydrogen transitions from a gas into a liquid, and deeper still, into metallic hydrogen. The winds driving the belts and zones flow all the way down to that transition point. Below 1,900 miles, the interior appears to rotate as a solid body, or at least it moves far more uniformly than the chaotic storm systems above. This discovery reshaped scientists' understanding of how gas giants work. Jupiter isn't just a ball of gas with weather on top. It's a dynamic system where atmospheric flows penetrate thousands of miles into the planet, interacting with the deeper layers in ways we're only beginning to understand. One of Juno's primary goals was to measure how much water exists in Jupiter's atmosphere. Water is a key ingredient in understanding how Jupiter formed. If Jupiter accumulated most of its mass through gravitational collapse, it should have relatively little water. But if it formed through core accretion building up from icy planetesimals, it should be water-rich. In 1995, NASA's Galileo spacecraft dropped a probe into Jupiter's atmosphere. The probe measured the composition of the gas as it descended. But the results were puzzling. The atmosphere at that location was surprisingly dry, with far less water than expected. Scientists suspected the probe had simply entered an unusual region, a dry spot. Juno's microwave radiometer could measure water content across much larger areas, and the data confirmed Jupiter's atmosphere is not uniformly dry. Near the equator, water is much more abundant than the Galileo probe detected, but the concentrations vary dramatically from place to place. This suggests that water on Jupiter isn't evenly mixed. Instead, it's concentrated in certain regions, possibly linked to storm systems or atmospheric dynamics. The discovery solved the mystery of the Galileo probe. It had simply landed in the wrong place. But it also raised new questions about how Jupiter's atmosphere circulates and how water moves through it. Juno was originally designed to complete 33 orbits around Jupiter. That would have been enough to map the planet's gravity field, magnetic field, and atmospheric composition. But early in the mission, engineers discovered a problem with the spacecraft's main engine. Some valves weren't working as expected. Rather than risk a catastrophic failure, mission planners decided to keep Juno in its original 53-day orbit instead of shortening it to 14 days as originally planned. This extended the mission timeline significantly. But it also opened new opportunities. The longer orbits allowed Juno to explore the far reaches of Jupiter's magnetosphere. And as the orbit gradually evolved due to gravitational interactions with the moons, Juno was able to conduct close flybys of Ganymede, Europa, and Io. NASA extended Juno's mission multiple times, first to 2021, then to 2025. By September 2025, Juno will have completed more than 50 orbits. At that point, the spacecraft's orbit will naturally degrade. Jupiter's gravity will pull it closer and closer to the planet. Eventually, Juno will plunge into Jupiter's atmosphere and burn up. This isn't an accident, it's intentional. Juno could still be carrying microbes from Earth, dormant bacteria that hitched a ride on the spacecraft during assembly. If Juno were to crash into one of Jupiter's moons, particularly Europa or Ganymede, both believed to harbor subsurface oceans, it could contaminate those worlds with life from Earth. So instead, Juno will be destroyed. The same fate befell NASA's Galileo orbiter in 2003 and Cassini at Saturn in 2017. Planetary protection protocols demanded. Juno arrived at Jupiter with a list of questions. How deep do the atmospheric bands extend? Does Jupiter have a core? How does its magnetic field work? Where do the auroras come from? Some of those questions have been answered, We know now that Jupiter's winds penetrate nearly 2,000 miles deep. We know the planet has a fuzzy core, not a solid one. We know its magnetic field is far stranger and more complex than any simple model predicted. But other mysteries have deepened. Why do the polar cyclones stay locked in geometric patterns? What drives Jupiter's lopsided magnetic field? How did the fuzzy core form? And why hasn't it collapsed back into a compact nucleus? And then there are the discoveries no one anticipated. The Great Blue Spot, the extreme volcanism on Io, the long-term stability of the circumpolar storm systems. Every answer Juno provided opened new questions. That's how planetary science works. Jupiter remains an enigma. We've learned more about the planet in the past decade than in the previous century. But the more we study it, the clearer it becomes how much we still don't understand. Take the core. Juno proved that Jupiter's interior isn't neatly layered. Heavy elements are mixed throughout a vast region spanning half the planet's radius. But how did that mixing happen? Was it gradual, a natural outcome of planet formation? Or was it violent, the result of a massive collision billions of years ago? Computer simulations can't decide. Both scenarios are plausible. Both have problems. Or consider the magnetic field. We know metallic hydrogen generates Jupiter's magnetism. We know deep winds interact with that field, causing it to change over time. But we don't know why the field is so lopsided. We don't know why certain regions, like the Great Blue Spot, have such intense magnetic flux. And we don't know how the fuzzy core affects all of this. Then there are the polar storms. Scientists have proposed several explanations for the geometric patterns: anticyclonic wind rings, deep convective flows, wave-like instabilities in the atmosphere, but none of these theories fully explain the observations. The storms remain stable. They oscillate slightly, perturbations rippling from one cyclone to the next. But they never merge. They never drift away. Why? No one knows for sure. Juno's discoveries reach beyond Jupiter. If Jupiter has a fuzzy core, what about Saturn? What about the ice giants, Uranus and Neptune? Scientists reanalyzed data from NASA's Cassini mission, which orbited Saturn from 2004 to 2017. By studying subtle waves in Saturn's rings, they probed the planet's interior. The results matched Juno's findings. Saturn also has a fuzzy core. This suggests that fuzzy cores aren't anomalies. They may be the natural state of giant planets. And that changes how we think about planet formation throughout the galaxy. Thousands of exoplanets have been discovered in recent years. Many of them are gas giants, some even larger than Jupiter. For decades, astronomers modeled these worlds using simple assumptions: a compact core wrapped in layers of gas. But if Jupiter and Saturn don't follow that pattern, why would exoplanets? Fuzzy cores change everything. They affect how planets cool over billions of years. They alter the distribution of heavy elements. They influence magnetic field generation. And they raise a fundamental question. If we've been wrong about the two giant planets in our own solar system, how many other assumptions need to be reconsidered? Juno's mission will end in September 2025, but the exploration of Jupiter is far from over. The European Space Agency launched a mission called JUICE in April 2023. It stands for Jupiter, Icy Moons Explorer. JUICE will arrive at Jupiter in July 2031. Its primary targets are Ganymede, Callisto, and Europa, the three largest icy moons. NASA is also sending a mission, Europa Clipper. Launched in October 2024, Europa Clipper will reach Jupiter in April 2030. The spacecraft will conduct dozens of flybys of Europa, using radar and other instruments to probe beneath the moon's icy shell. Scientists believe Europa's subsurface ocean could harbor life. Europa Clipper will search for signs of that ocean. It will measure the thickness of the ice. It will analyze plumes of water vapor erupting from the surface. And it will test the radiation environment, paving the way for future missions that might one day land on Europa and drill through the ice. Jupiter's moons are worlds unto themselves. Io, with its endless volcanism. Europa, with its hidden ocean. Ganymede, the largest moon in the solar system. with its own magnetic field. Each one offers a unique window into planetary science, and each one has secrets still waiting to be uncovered. Jupiter holds a special place in the history of the solar system. It formed early, within the first few million years after the Sun ignited. Most of the material left over from the Sun's formation went into building Jupiter. And because the planet is so massive, its gravity was strong enough to hold onto its original composition. That makes Jupiter a time capsule. Its hydrogen and helium came from the same cloud that formed the Sunday. The heavy elements mixed into its core were present in the earliest days of the solar system. By studying Jupiter's interior, scientists can learn about conditions that existed 4.6 billion years ago. How much water was present in the outer solar system? How were heavy elements distributed? How quickly did planets grow? These questions aren't just about Jupiter. They're about how the entire solar system came to be. And the answers could help us understand planetary systems around other stars. Every discovery we make at Jupiter has implications far beyond one planet. When Juno launched in 2011, it carried with it decades of unanswered questions. How deep do Jupiter's storms go? Does the planet have a core? What generates its magnetic field? After more than 9 years in orbit, Juno has transformed our understanding of the largest planet in our solar system. We now know that Jupiter's atmosphere is far deeper than anyone expected. We know its core is diffuse, not solid. We know its magnetic field is complex, asymmetric, and changing over time. We've seen the polar cyclones locked in their strange geometric dances. We've measured the most powerful volcanic eruptions in the solar system on Io. We've watched the Great Red Spot shrink and revealed its hidden depths. But perhaps Juno's greatest legacy isn't the answers it provided. It's the questions it raised. Every discovery has pointed towards something deeper, something stranger, something we don't yet fully understand. And that's what drives science forward. On a clear night, Jupiter is easy to spot. It's the brightest object in the sky after the Moon and Venus. A steady, unwavering point of light. Through a small telescope, you can see its 4 largest moons just as Galileo did more than 400 years ago. Through a larger telescope, you can make out the bands of clouds, the swirling storms, maybe even the Great Red Spot if conditions are right. But what you can't see is everything beneath. The metallic hydrogen ocean, the fuzzy core, the auroras flickering at the poles, the cyclones spinning in perfect geometric patterns. You can't see the 400 volcanoes erupting on Io. You can't see the subsurface ocean hidden beneath Europa's ice. You can't see any of it. That's why we send spacecraft. Juno gave us a glimpse of a world far stranger and more complex than we imagined. And when the spacecraft plunges into Jupiter's atmosphere in 2025, burning up in the same clouds it spent years studying, it will leave behind a legacy of discovery that reshapes how we think about giant planets everywhere. For now, all we can do is watch and wonder what we'll find next.